So clearly we need to put the numbers in the correct spots here. And while you could do that many ways, there does seem to be a most efficient way, and that is to start with this intersection of the sets A and B and U, this inner intersection. So you start from the inside and go out. Seems to be the easiest. So what is common to A and B? Well, if you look at problem 15, it looks like they have a 6 in common and an 8 in common. And so we'll put the 6 and the 8 here. We're going to work our way from the inside to the outside in general. It's easiest that way. A has one other number in it. So now notice the circle A has 1, 6, and 8 in it, like it's supposed to. B has 2, 4, and 7. So now B has the right things and A has the right things. But the universal set's supposed to have 1 through 8. So what's remaining for outside of A and B? Well, we've got 1, 2, we're missing 3. We've got 4, we're missing 5. And we're missing 6. So it looks like we need to have 3, 5, 6 on the outside. Now let's check. Does A have 1, 6, and 8? Yes. Does B have 2, 4, 6, 7, 8? Yes. Does the universal set, which is everything, contain all the numbers from 1 to 8? 1, 2, 3, 4, 5, 6, 7, 8, except we don't need 6, so it's a good thing we checked. So it looks like we're done. This symbol stands for intersection. So the set A intersect the set B is a set that contains everything that's in both A and B. And so we have things that are in A and B. Well, we have a picture, a Venn diagram, and it looks like A and H are in the intersection, so we're done. Here we want the intersection of two sets. The first set is everything in the universe outside of the set A, and the second is everything in the universe outside the set B. This is called the complement of A and the complement of B. So the intersection of the complements will be the intersection of these letters, which are all outside A, and these letters, which are all outside B. And if you look at this list fairly closely, I think you'll see that the intersection are just these three. And so the intersection, once again, is a set. It's the set P, M, Z. Now, it's kind of interesting that those three letters are the three letters that are not in A and not in B. Do you think that's a coincidence, or do you think that there's a reason for that? So think about this. These are all the things not in A. These parts were in B. These parts were not in either. These are all the things that are not in B. These parts were in A only, and these were not in either. So when you take the intersection, these are never going to have anything contributing to the intersection. These are always completely separate. So it seems to me that in this case, it's reasonable that this notation means basically all the elements outside of the sets A and B. Problem 51, we want the intersection of two sets. The first set is the complement of A, that's everything not in A, everything in the universe not in A, intersected with B. Well, that seems to be everything that's in B that's not in A. And that would be, from the picture, everything in B that's not in A would be 3, 5, 6. So let's see if it's true. We got 3, 5, 6, 3, 5, 6. We got a 2, 9 here. We don't have any 2 9s there. So the intersection, once again, is a set. It's the set 3, 5, 6. And it's no coincidence that 3, 5, and 6 are the elements of B that are not in A. This kind of notation seems to do that.